Hi, everyone. My name is Zixuan. I'm from Technical University of Munich, and I'm here to talk about PepSi. First, why? So, as you see, I'm from Thun. Here is a map of Germany, annotated by the number of breweries, and this is where our lab sits. Of course, we sit at a region where we have the highest density of breweries. That's why our lab has been dedicating ourselves on developing tools centering around beer. We have Prosit, Koina, Oktoberfest. That's all like beer stuff. However, we are a very inclusive lab, and we're well aware that beer is not for everyone. That's why I started this new franchise for people that are not really fan of beers, especially myself. Here comes PepSi then. But jokes aside, why actually are we doing PepSi for peptide intensity? So the real reason is that our lab and so far the whole community has been rather focusing on MS2-based evidence for peptide and protein ID and quant. And with PepSi, we're here trying to shift the focus from MS2 to MS1, from fragmented peptide to intact peptide, and hence infer protein informations. Just for the people here that is more involved in the metabolomics field, here is a quick overview of a classic bottom-up mass spec-based proteomics workflow. You start with a proteome sample, and then you digest it with protease of your choice, and then you get a pool of peptides. The peptides are going to shoot through a liquid chromatography, and then they're going to elute little by little. For every time step in your LC scan, you take a snapshot of the peptides that are being eluted together, and then you get your MS1 scans. And then among the peptides that is being taken in this group picture, you can select, not you, but some of the lucky peptides are going to select it to be isolated and fragmented, and then generate these so-called MS2 scans. And then from the MS2 scans, we can kind of sequence the peptide and get peptide identities. And from MS1, we mostly just get a quant. There are, sorry, that was too fast. There are two main caveats of the current work. First of all, from the peptide to the protein inference step, we're essentially doing heuristic here. We're kind of implicitly assuming that peptides have all equal intensities, which is almost never the case. And for inferring a protein, we rely on the top score peptide of the protein, and the protein ID and quant are often only resolved at protein group level. And the second caveat is on how we use the data, because most of the ID information actually comes from MS2, or I can even say all, if you do not do match between run. But as I said before, the MS1 is a group picture of all the peptides, and MS2 is just solo pictures of some of the lucky ones. So MS1 is actually very informative, but we only use it for quant so far, so it's really an unfortunate underutilization. That's what we're trying to tackle here with PepSi. Nowadays, it's almost a standard practice to use fragment intensity predictions to improve peptide identification from MS2-based evidence. So we thought, why not do the same? But for MS1 information, why don't we just use peptide intensity predictions to directly improve protein IDs from MS1-based evidence? It almost seems like a one-to-one mapping. For now, with the MS1 informations we have already, NZ, we have retention time with very good predictions, and sometimes even ion mobility. The goal of PepSi is to introduce this extra dimension of intensity, which turned out to be very informative for PSM, peptide spectral match rescoring. How about for MS1 then? So then how do we formulate a problem? Again, we take a look at how the community has been tackling MS2. So for MS2 intensity prediction, you essentially have a sequence input and then you get a vector output. It is relatively straightforward in terms of fragment ion annotation, because your peptide length usually spread nicely between 7 to 50 the majority is actually below 30. So there is clear way of defining Y1, B1 all the way to Y29 to B29, and then you have very clear annotation. And very luckily, all the fragment ions are usually captured in one single MS2 scans. That makes everything easier. But how does it look like for MS1? So for starters, it's actually not so nice. Here you can see that in this scatter plot, it's actually a very selective example of one MS experiment. In x-axis, you can see retention time. So all the peptides that belong to the same protein actually scatter over the whole retention length. And they're usually not, almost never captured in one single MS1 scans. And we also have protein length that is ranging across a much wider range compared to the 7 to 30 for peptide lengths. So this sequence input and vector out solution does not really work. What do we do instead is that we use pairwise intensity. So the idea is we take a protein, we digest it, and then we measure it into our tandem mass spec. And then we usually only get to identify and quantify a very small portion of it. But from this very small portion, we generate pairwise input exhaustively. And we essentially are predicting here the log2 fold changes between intensity of peptide A and B. So this is how we define the problem. By this, we actually simplify the problem a lot because we are bypassing essentially the precursor ion annotation problem. And as a nice side effect, because of the pairwise combination, we also really gain a lot more training data. So the next question to answer is that this is all like nice and seems promising, but is it actually possible to even model it? For that, we had a look at the pairwise intensity of experimental data. First, we aggregate different raw files where the same proteins are measured multiple times, and then we aggregate the peptide pairs to form a pseudo-ground truth, and then we evaluate how much deviation are we looking at from different measurements to the pseudo-ground truth. And here we can see that we have a medium of 0.3. That is to be considered in a log2 fold change range of -10 to 10. So it's actually not too bad. And the next thing we're looking at is the pairwise correlation of this so-called peptide intensity fingerprints of the same protein in different raw files. Ideally, we want to see that they're close to 1. And here we do see the medium of such a correlation is around 0.9. So it's somewhat consistent and it should be possible to model this. The next thing I would like to quickly talk about, I don't want to bore you with all the detail in the implementation architecture. It's bad enough that I have to go through it myself. So we have a pair of peptides as input. We pass them through identical Siamese arms, and then where these hidden representations are generated, and then we do a quick, simple little subtraction, and then we pass it through the regression head where we get a final log fold change predictions. And for training, I am very lucky to get my hands on this awesome data set that contains 303 bacteria species. So it's actually very brief amount of peptide sequences that we're covering here. And in the end, it amounts to, so after all the filtering, pre-processing, etc., we end up with 28 million training peptide pairs, which is actually quite nice. And then after quite some time of training, we finally get our first version of the model. And the model performance is also shown in comparison of the consistency evaluation I've done before. So in terms of absolute prediction error, we're looking at a medium of 0.65. Again, I remind you, it's for a range of from -10 to 10. So it's okay, I would say. For the correlation of protein fingerprints, we're looking at a medium of 0.74. But these are all a bit abstract, I understand that. Now, the next thing we try to do is we take these predictions and then we try to put it into an application scenario. What we do is essentially we're trying to do MS1 only identification here. We need to start with feature engineering. So how does that work? We take the pairwise intensity prediction from PepSi, which is shown in this heat map here. It's only upper diagonal because the prediction is more or less symmetric. And then we take the observations of all these pairwise peptide intensities, and then we overlay them and do a little subtraction. We then get prediction error. We do see that in the last figure here, there is already two somewhat distinct clusters. So what are those? We also pull out the MS2 base evidence. And here the x-axis is the Andromeda score from XQuant, and y-axis is the precursor ions. The orange one is the decoys. So we can clearly see that the last three columns are actually decoys, and the last column here, it's not a decoy, but it's a very low score target, so it's likely a false positive target. So it worked to some extent, not perfect, because you do have decoys that is somewhat kind of get mixed into the target. But how does it work if you include it into a complete workflow? So the workflow looks like this. We start with a feature detection algorithm. Here we use Biosor. That is from another group several years back. And this Biosor gives you a list of MS1 features, which you can then pass to a MS1-based search engine that is called MS1 Search Pi, which then gives you a list of peptide feature matches. And with this list of peptide feature matches, you can pass them into rescoring tools such as Percolator or Mockapot, which then can generate this nice Q-value peptide level here, peptide identification plot here. The x-axis is Q-value, or essentially FDRs, false discovery rate, and y-axis is the number of target peptides that we're accepting at this specific level of FDR. This line here shows first the original features generated by MS1 Search Pi. We can see that at 1% FDR, which is the favored number by the community, we don't really get any identifications. But what if now we include PepSi-based prediction errors? Boom, you actually do start to get useful identifications, a good amount of them. And in comparison of MS2-based evidence, which is the green line here, we're not quite there, but not that far. And with all this, keep in mind that we're only using all the MS1 information from an experiment, which takes about 25% of your acquisition time and only 5% in terms of scan number of your whole raw data. And next step, we want to use it for protein level scoring or identification. What we can do is here an intensity-informed scoring, which is in contrast to how the people are doing it now without the intensity information. We start with the full protein sequence, we in silico digest them, and then we get a list of all the peptides and their PepSi intensity predictions. And if we sort all these modeled peptide intensities, we can get a mirror plot like this, where below we get the expected or predicted intensity, and above we get observed ones. For a target protein, it should somewhat look like this, because we do expect that if you predict a peptide to have high predicted intensity, you're very likely to observe them as well. That's why here you see that the observed peptides are kind of enriched somewhere in the left side of the plot. And for a decoy protein, we expect it somehow to distribute uniformly in a random way. It does look like so in this small example. What does it then, how does it look like if we integrate it into the complete workflow? So up until here, we get a list of PFMs, peptide feature matches. And from this peptide feature matches, we can start calculating protein scores. And then with the protein score and a couple other features, we can do rescoring again, but on protein level. So first, again, a plot without PepSi information, without intensity informed scoring. And then if we do it, we again get a performance boost. And this is the results in comparison with MS2 base intensities. Still getting close, not quite there, still using only MS1 information here. So as a summary, what we find out is that protein fingerprints, they're actually somewhat consistent, and it's actually possible to predict them in the form of pairwise intensity. And with all this, we do find out that it's possible to enable MS1-based peptide and protein identification at reasonable FDR level. For the future, we have a lot other things on our to-do list. We want to explore other applications, for example, to increase match between RON or peptide identity propagation confidence. We want to do protein group deconvolution. We also want to, I also want to mention that such a model is usually very workflow specific. If you think about it, it's actually a black box that is wrapping from sample preparation to the actual acquisition methods, everything in between is being captured in this model. So it could be that your sample preparation workflow is a bit different than the training data set that we're using here, or that you're using a completely different machine. All of this have an impact on the results. That's why we are also looking into ways to do transfer learning and fine-tuning with smaller data sets to enable the possibility to use such a model, even if you don't have 340 raw files to train it. And we're also trying to work out compatible MS1 only acquisition or MS1 focus, because if you only use MS1 information, why waste all the time acquiring MS2s? And we are also thinking about how to incorporate modification information into the model and many other things. This is only a start. With this, I would like to conclude my presentation. I would like to thank Wilhelm Lab for all the support, discussions, infrastructure, everything. Thank you very much.
Thank you. Very nice talk. I think I have to run again. Sorry to be here.
Thank you very much for the talk. Actually, I found it really fascinating, because usually when you talk about recognition of peptides or so, you always talk about MS2. So I have a particular question regarding PTMs. Because usually I think that's one of the huge things about identifications of peptides that, when you look at fragment level, so you look for identification of deltas in mass. So how does an identification only from an MS, perspective will work in order to, let's say, identify, PTMs and proteins and peptides, etc.? So.
Yeah, so to answer your questions, I would say the tackling of PTMs would have been a very similar way to, as in tackling naked peptides, but we just need to find a different way to encode it. If we manage to encode it, I think there should still be a problem. If we manage to find a way to encode it, I think the model would be able to learn it if there is enough data, as long as they do have an impact on the intensity that is generated from it. If that is not the case, for example, if different localization of a PTM is somehow not generating any impact of how good a peptide gets ionized, hence no information in intensity is being manifested here, then there wouldn't be, it wouldn't be possible.
Follow-up with respect to that. If it's only based on intensity, right? That would imply that, as you mentioned, only.
Thank you. Sorry. So if it's only based on intensity, that will imply that only PTMs that have an impact on the spectrum MS1 will be recognizable. But there are a lot of PTMs that actually are not, that we know that are available, that are documented that exist, but they don't have a strong impact on intensity. So will that have any impact on the results that you will get, maybe missing, PTMs and so?
I mean, if it doesn't have an impact on MS1 intensities, then by definition, this is not something that we can tackle with such a model.
Thanks.
We'll do a quick question from online, and I propose that you then can chat during the break. So were decoys included in training, and how does the model perform on co-eluting peptides?
So the first question, it's actually a really good question. Decoys are not included in the training. But it actually would have been very useful because the model should somehow learn that some peptides are not to be observed and hence do not have an intensity. So far, we're not doing that because we haven't found it very reasonable way to to generate meaningful label for decoys. Not sure if just putting 0 is the right way. And then the second question, co-eluting peptides. I hope in our training data they're not the majority, because we are actually not actively tackling them right now. But this is actually very interesting. Our group do have another tool that is also from me. It's called SWAPS, that is looking into this kind of problem. We're actually using quite long gradient for our training data. We hope that this does not happen because that's kind of mess up the intensity values that we use as our clean training label. But in the future, this would be taken into account if we're ever going to incorporate training with shorter gradient data.
Okay, thank you very much.
Thank you.